Okay, I guess we can start. So today we're going to start talking about duality, which is like a really important component of the course. And in fact, in a sense, just by an analogy, if you remember like linear algebra, like almost like the first half of linear algebra is very computational because it's very computational because you're learning how to use like row reduce a matrix, how to identify uh, systems of equations and all that stuff. And then it kind of gets a little bit more abstract when you start talking about vector spaces and a basis dimension. And this course is somewhat similar to that, where um, like the simplex method is definitely the most computational part of the course. Now we're switching gears a little bit and talk about duality. Yeah. Uh-huh. Oh, I didn't mean it for today. Did you email me about the date? Oh, I mean, yeah, if you can email me, but I wasn't planning it for today. Yeah, yeah, yeah. Probably next week, if that's okay with you. We could do it next Tuesday, for example. That's fine. But yeah, email me because like yeah, otherwise, yeah, like don't worry about that. Yeah. Mm. So So as I was saying, like this part is definitely more theoretical. So it is useful to keep an eye on it because the flavor of like the problems are very different from the ones that we have been working on. So I'll also giving you more like constant problems for you to work on because it does take more time to get used to it. And we will move between theory and application. So I'll probably do some applications to probability theory next week with Markov chains because it's like we kind of have to like see it is like an important idea, and like the reason why it's important idea is because they have like very different uses. So I will kind of like oscillate between like giving you like a result and then applying it to something, and so I'll kind of like give you some brief intro to probability theory, like maybe next week, I would say. Um, okay, so before telling you what the idea behind duality is, which I had mentioned briefly on the first day of class, then I do have to mention something about like the transpose of a matrix because when it comes to duality, the transpose plays an important role. So we should talk about why the transpose of a matrix is useful. So, well, so just to like start with something simple, like just like to give it like specific values, if you remember like the transpose, what the transpose does is like change rows into columns, right? So like the rows becomes the columns and so on. So that's A and that's A transpose. So A is 2 by 3 and the transpose is 3 by 2, right? So in general, if A is m by n matrix, right? Then the transpose, A transpose is n by m. That is how this works. Now, that doesn't really explain why the transpose is a useful concept, right? So why is the transpose? I mean, it seems like a natural thing to do, but why is it a useful idea? So let's just talk about that for a second because I don't necessarily think whenever you talk about this in linear algebra, that you kind of go into this discussion. Sometimes you do, and other times you don't. So why is A transpose useful? Okay, so the main reason is that the transpose kind of like interacts nicely with the dot product. And I'll explain what I mean by that. Okay, so let's talk about the dot product for a moment, which we have used a couple of times, but like every time you do a matrix multiplication, you're doing dot products, but like it's useful to kind of rewrite it in different ways, and you'll see why the transpose works well with it. But so if you have two vectors, right? Let me recall the dot product. Let's say you have two vectors. Okay, I'll write them as columns because that's like the usual convention. A bit annoying, but it will be useful in a moment. So let's say u1 up to un, that's the first vector, and then the second vector is v1, v2 up to vn, right? So if you remember the dot product, the dot product is just like you multiply the corresponding entries and then add, right? So like you do u1 u1 v1 plus u2 v2 plus u3 v3 plus un vn. Okay. But there's actually two ways to write the dot, which by the way happens to be the same as v dot u, right? What's kind of nice is that there are two ways to write the dot product using matrix multiplication, right? So um, so one way is the following. If you look at u dot v, okay, now whenever you want, you can think of a vector as a matrix. It's a little bit of an overkill most of the times. But in this case, like if you do that, what types of matrices are these? They have n rows and one column, right? So these are the two n by one matrices, right? You cannot multiply them directly as they stand, right? Because like the rule for multiplying matrices, if you remember, is that these two numbers must agree, right? Like the last and the first numbers like of the sizes must agree. But you can take care of that by reversing one of them, right? So one way to think about one way to try to do like a matrix multiplication here would be, for example, to turn the vector u into a row vector, right? I'll actually drop the arrows because I want to emphasize that now I'm thinking about this as matrices. So I think about this as a matrix, right? So if you transpose it, that would have been like 1 by n, right? And if you multiply it by the vector v, which is n by 1, right? And here I literally mean matrix multiplication, right? I'll write it explicitly. I mean, you can kind of say that the matrix, I mean, the matrix, like, it depends on how you studied this for the first time, but to do matrix multiplications, you're basically just doing a bunch of dot products. So this shouldn't come as a surprise, right? So in this, but if you kind of like look at it, something that's 1 by n times n by 1, the matrix that you get is 1 by 1, and a 1 by 1 matrix is a scalar, so you get a scalar, and the dot product is supposed to be a scalar, right? So one way to write the dot product is as the vector transpose times the other vector. Is that making sense? Kind of like questions about that so far so good. It's kind of like I'm just it looks a bit silly, but it's like a convenient way to write the you know. You're good. No worry. So in terms of matrix multiplications, the way to write the dot product, is that u dot v is the same as u transpose times v, and which is kind of fun because it doesn't matter in which order you do the dot product. You could also have written this as v transpose times u. So it doesn't matter which one you transpose, right? You just have to put them in the correct order so that you can do the matrix multiplication, and you get a 1 by 1 matrix. So that is like a first explanation because it's kind of like telling you that the transpose kind of like allows you to write the dot product in clever ways, with like this operation of multiplication. So this is like if you want to call it reason one, this is reason one for why the transpose is useful. Okay. Is that okay so far so good? Everyone with me? And then reason two, which is like the really cool one, is I don't know if there's like a specific name for it, but is like the moving into okay. Definitely this is not standard terminology, um, but I'll explain what I mean in a moment. So like the other reason why the transpose is convenient is because it allows you to move the matrix to one of the other two factors. So what do I mean by that? So okay, let's see if this is making sense. So you imagine you had two vectors, right? You have two vectors, but before taking their dot product, you choose to multiply one of those two vectors by a matrix. Okay? So you like instead of doing u dot v, I choose to multiply u first by a, right, by a matrix. That gives you a new vector, right? Because remember, matrix times vector is a vector. So I produce a new vector using a matrix, right? And then I take the dot product. Okay? What the transpose allows you is that if you notice here, the matrix A appears in the first factor, right? It appears in the factor U, like for the vector U. Well, the transpose allows you is that you can move the matrix A to the second factor, but if you move it to the second factor, you have to transpose it first. So that's what I mean by moving to the other factor property, because you can kind of like locate the matrix either in the first or the second factor, but you just have to transpose whenever you switch your minds. So kind of like writing it makes it more clear what's going on. So what I'm saying is that if you, for whatever reason, you didn't want to see the matrix A multiplying the first vector, you are allowed to multiply the second vector, but the price to pay is that you had to transpose first. Okay. So like in words, if you want to move the matrix from the first factor to the second factor or to the other factor, you have to transpose it. So you can move the matrix from the first factor to the second one, provided you transpose first. Is that making sense? Kind of. And now, why is it true? Like actually, like the proof is like a one-line proof, but it's kind of like cute to see. So why is this true? Like basically, because of what I just wrote of reason one, because what is AU dot V? Oops, like let me. Well, if you look at the first property, right? What does the first property say? It says that if you want to write out a dot product, you can write it as matrix multiplication provided you transpose the first factor, right? So you can write this as matrix multiplication if you transpose the first factor. Is that okay? Is that making sense? But I don't know if anyone remembers like the property that the transpose has for a multiplication. The transpose of a product is the product of the transpose but reversed, right? Like let me write it on the board. If you remember, AB transpose is B transpose A transpose. You know, like you can transpose each individual factor, but you have to flip it. So if you do that, this is you transpose A transpose times V, okay? Which is U transpose times A transpose V. But if you look at it, that is essentially what U transpose, sorry, U dot A transpose V would be. Okay. So it's kind of like very clever, but so essentially this works. So what I'm saying is that so we use here that A V transpose is V transpose A transpose. Yeah.
But you applied the transpose to AU, but you didn't apply it to B.
Well, right, because if you look at the if you look at the at the first box that I wrote here, right? When you have a dot product, you only have to transpose one of the two factors. You're free to transpose whichever you want. I used the first version of the formula where I transpose the first factor u. It's just that in this case, like the first factor happens to be a u, right? Yeah, yeah. No worries, of course. It's kind of cool. Like if you wanted to do this very elegantly, in fact, if you really want to do this like in a clever way, you did find the transpose of the matrix by that formula, and then you show that that corresponds to switching the rows into columns. You kind of like, it's kind of like taking like chicken egg, like going backwards, like, instead of like saying, oh, let's just turn rows into columns, it's like, no, I want this very clever property to happen. And that forces the matrix to be the one that you obtain by reversing turning rows into columns. That is like kind of like the nicest way to do it, but in practice, it's like a little bit too abstract to kind of like mention it like at the in a intro to linear algebra class. Uh, but yeah, like that's kind of like but that kind of like hopefully it kind of gives you like an idea of why the transpose is related to dot products, because they do kind of go well together. Like, they behave nicely with one another. And that would be useful because if you remember in the optimization problems, why is the dot product useful? Because like the functions that we were maximizing or minimizing could be written as dot products. So that's how this connects to what we have been like. It looks like completely separate to what everything I have been said so far. But remember, the dot products secretly were in the picture because the functions we were maximizing or minimizing could always be written as dot products. So why am I like, let me write that down as well. Why am I bringing this up? Am I bringing this up? Because the functions we were maximizing uh, were written as dot products. In fact, if you remember, like the standard way how I wrote the optimization problems were like we were looking at the max of C dot X, right? Where X had to be non-negative, meaning that every entry of the vector of variables was non-negative, and you had like these inequalities that AX was less or equal to B. Like that was like the standard way how I wrote the system of like maximum problems that we were working with, but there was always like this dot product vector that we were using uh, when we were writing the max min problem, which we tested on the first exam. Like we really didn't use this on the second one, but like secretly it was there. And this property will turn out to be useful for something that's called weak duality, which I may have time to talk about today. If not, I'll definitely do it next time at the beginning of next class. Um, okay. No. Okay. Okay, so now I can start talking about duality. By to start doing that, like I'll remind you the first time where I mentioned this, which was like on the first week of class. So like it was a long time ago. So I'll kind of like give you like the basics of what I had said that day or during the first week. So we had talked about this like farmer's problem, if you remember it. So now let's start talking about duality. So back to the original problem of like the course, which was like this farmer's problem. I mean, I'll kind of like summarize a little bit of the story, but you were selling potatoes, carrots, there were some restrictions, like whatever, like I'll just write them. Um, you were trying to find the max of this function, right? Where x1 was greater or equal to 0, x2 was greater or equal to 0. I think x1 represented the number of potatoes you were going to sell, and x2, or the number of seeds that you were going to grow with potatoes, and the other one was for carrots. And the conditions were that, x1 was less or equal to 3,000, and that x2, well, let's do it, let me drop the thousands, like just to, so just imagine this is measured in thousands. So x1 was less or equal to 3, x2 was less or equal to 4, and x1 plus x2 was less or equal to 5. Okay? Okay, so now you're experts in the simplex method, so you could totally attack this with the simplex method. But like, the reason why I had done it in the first week of class is because you could just draw it out, right? And when we had drawn it out, like I'll just remind you how like the graph looked like, or the region, the polyhedra. If you draw this out, you ended up with something like this. This was the region. And if I'm not mistaken, the max, right? Like the max occurred here. Oops. This was the point that yields the max, the corner that gives you the max, and the value for the max in this case, well, it would be 1.2 plus 4 times 1.7. 4 times 1.7 is 6.8, and 1.2 plus 6.8 is 8. Okay, so the max in this case was equal to 8, and in the 8,000, because originally in the first week of class I did it without everything was with thousands, but at point 1.2 comma 1, sorry, 1 comma 4. Is that okay? So far, so good. That looks familiar. Okay. Now, where had I brought up the duality stuff in this problem? So what I had said is like, what I had said, like the motivation for the duality, the way it happened in this problem is like, imagine for a second that you forgot how to graph. So you don't know how to graph, you don't know how to find the max graphically, and you forgot the simplex method, right? So you don't know like the simplex method, you don't know how to graph. So how would you try to work to determine the max? So one alternative approach that you could have done is to try to see whether from these inequalities, right? Just playing with the inequalities, whether you could try to find so at least tell me that the function that you're trying to maximize is not that much larger than 8. So the duality comes in. Okay, like let me start. I'll remind you a little bit of what the setup was. So the idea of the duality is that you try to find the max from the inequalities themselves, from the inequalities without solving the without using the simplex method, let's say. Okay, so how did this work? Like for example, run some cases for what we had done. So let's say that you just look at the first two inequalities, right? So I'll just focus on inequalities 1 and 2. Okay. Let's say I multiply inequality 1 by 1.2, right? Why would I multiply by 1.2? Because like the function involves 1.2 of x1, right? And so you would do 1.2 of on both sides of the inequality, right? And what is 3 times 1.2? That is 3.6, if I'm not mistaken, right? And well, let's say I multiply both sides of the second inequality by 1.7, right? Why 1.7? Because 1.7 is literally the coefficient that appeared in the second like factor, right, of the function. So you would get 1.7 x2 less or equal, what is 4 times 1.7? I think I said it before, like that's 6.8. Is that okay? Is that making sense? And then if you add, right, if you add both inequalities, right, like you can add both inequalities. So now you add them, and then you get that 1.2 x1 plus 1.7 x2 is less or equal than 3.6 plus 6.8, which is like, I think 10.4, if I'm not mistaken. Right? Is that making sense so far so good? Looks familiar, refresher. And this is cool because like, it's saying like only from these two inequalities, you know for a fact that the max could not have been more than 10.4. In fact, we know better, right? Because we do know that the max is 8. But like this is kind of like the first approximation to how big could the max have been. Because again, I'm not trying to solve like the system, right? Like I'm just playing with the inequalities directly. Let me do the second one, which was a slightly more clever approach, right? Just to show you that you could like you could have like done like a little bit better. So here I'm going to use like the three inequalities. Okay, I'm going to multiply the first one by 0.2. The idea is that I'll show you why in a moment, but basically I'm going to think of 1.2 as 1 plus point plus 0.2. So I'm going to multiply the first one by 0.2. So that gives you 0.2 x1 is less or equal to 0.6, all right? Then I'm going to multiply the second one by 0.7. Okay. So that gives you 0.7 x2. Okay, so what is 7 times 4 is 28. So it's like 2.8. Yes, I think so. Yes. And then I'm not going to do anything to the first one, to the last one. I'm just going to multiply by 1 so that I get x1 plus x2 less or equal to 5. Is that okay? And why am I doing this? Because again, if you add like all the three inequalities together, 0.2 with 1 adds to 1.2, right? If you add now, you get 1.2 x1, right? You get again 1.7 x2, right? But now when you add all these numbers together, you get 7.8 plus 0.6, that's 8.4. Right? which is an improvement, right? Because now if you this more clever combination, right, of the inequalities tells you that the max could not have been more than 8.4, which is better because we're cheating because we already knew the answer, right? Which should be 8, but like we kind of like narrowed the options to 8.4, right? Is that making sense? And okay, so now I can remind you what the dual problem in this case. Like the dual problem is, can you find a clever combination of coefficients, right? That, for example, would have given you literally 8, right? Like this bound would have been 8 and not 8.4 or 8.1 or 8, like, that would actually have given you the number that you were after, right? So here's like the dual problem. You have to find non-negative numbers because otherwise it flips the inequalities and it's like a mess. Like, you're always multiplying the inequalities by a positive amount so that they don't get flipped. So in this case, since there are 3 inequalities, I want to find numbers y1, y2, y3, right? Like those are like the multiplication coefficients. So can you find numbers y1, y2, y3, which are non-negative? And what's the idea with each of these? Again, like the idea is that each of the numbers is like the multiplication, like the factor that you multiply each inequality by. So the first one gets multiplied by y1, and so that gives you y1 x1 less or equal to 3y1. The second one gets multiplied by y2, so that gives you y2 x2 less or equal to 4y2, right? And the last one would get multiplied by y3, so that gives you, you know, y3 x1 plus y3 x2 less or equal to 5y3, right? And if you were to add those inequalities together, right? If you add now, what does that give you? Like just factor like terms. So factor these two together. So you get y1 plus y3 times x1 plus, and then factor the x2s here. Two. Okay. That should be less or equal to what? To 3y1 plus 4y2 plus 5y3. Right? So what are we trying to do? So this is how the inequalities look in complete generality, right? What we want to do is make this as little as possible, right? Because the more that you're shrinking this, the better like the bound is. So here we're trying to minimize instead of maximize, right? So what is the goal here? You want to minimize 3y1 plus 4y2 plus 5y3, right? And what are the conditions that this is subject to? This is subject to what? First, each variable has to be non-negative, right? Because as I was saying, like if you didn't make them non-negative, then it messes up all the inequalities. It's like a complete mess. You don't want that. And then, okay, so And if you look at how we were choosing them before, we were choosing the coefficients, we were not like before when we were choosing the coefficients, they were not chosen at random, right? They were chosen so that you would get back the numbers that appeared in you know, the numbers that appear in the optimization function. Otherwise, it wouldn't be useful to constrain the optimization function. So here, like, you don't necessarily need them to kind of like be exactly 1.2 and 1.7, but at least they should be as big as those so that they kind of help you constrain the optimization function. So the two inequalities that you would have are that 1.2 should be at least y1 plus y3, and that 1.7 should be less or equal to y2 plus y3. Again, in the previous two examples, no, they were exactly the same, but like you can be a little bit more flexible when you set it up, because usually like, working with inequalities, at least when you set up everything, is a little bit more natural. Um, yeah. And this is going to be called the dual problem to the original problem. What I'm going to do now is kind of like identify how everything changed, because that is where you'll see the transpose like appear. It's kind of like hidden in everything that I just did, but like you'll see it in a moment. So this is called the dual to the original problem. So this is like the dual to the farmer's problem. Making sense? Yeah.
Where did you get these two from? 1.2 is less than or
Well, so the thing is like again, like the way we were doing this before, right? You were like, I was choosing the coefficients so that they would give me 1.2 and 1.7, right? Because the optimization function had 1.2 and 1.7, right? So like this wouldn't, like, for example, if you chose like the number so that this gives you 0.5, that's not useful because you need this at least to be 1.2, right?
Oh, so those two have to add, okay.
Correct, right. So because otherwise, like you're constraining like something that doesn't control like the optimization function, right? Now to kind of like, so it is like like if you look at it from this perspective, it is kind of clear why it's related to the original problem, because the attempt here is to control, like, just from the inequalities, the max. But it maybe like this duality thing is not super obvious why it's called the dual. So for that, you do have to change to matrix notation to kind of like appreciate better what's going on. So I'll kind of like rewrite each of them in matrix version. And once you do that, you'll see, okay, like kind of like it's easy to extract one from the other. So, okay. So let's go back to the matrix notation. So let me just take the original problem. I'll take the original problem and put it in matrix notation. So in this case, what do we have to do? So there are two variables, x1 and x2. So x is going to be x1, x2. The vector c, right? If I want to write this as a max of c dot x, where x is greater or equal to 0 and ax is less or equal to b, the vector c in this case is just like the vector of coefficients, which is 1.2, 1.7, right? Actually, let me use colors for this because like that way it will be easier to identify how they changed. And the matrix A, well, what is the vector B? That's also easier to read. The vector B is just like vector of constants, right? So it would be 3, 4, and 5. And what is the matrix A? The matrix A, it would be 3 by 2, right? Because there are two variables. So A would be 1, 0, 0, 1, 1, 1. Is that okay? Is that making sense? So far, so good. How extracted everything from it. Um, okay, so now so this is called this is the original problem. Sometimes like in the literature, this is called the primal problem because it's kind of like the primary problem. So here's like matrix notation. This is like, again, the original or primal problem. Okay, so I'll use that, just throw that in. Because it's kind of like the primary problem, like the one that you were actually trying to solve. Now for the dual problem, which you could also call the secondary problem if you wanted, but for the dual, okay. So let's just write it down. Like I had it right here, right? So it like let me copy paste it first. Okay, so what's happening here? So the vector of variables, right? Now we have three instead of two variables, right? So the vector of variables is, I'll call it y, is y1, y2, y3. This will be confusing, but like, what is the vector of constants? Like, vector of constants is 3, 4, 5, right? 3, 4, 5 is what you had before. So I'll just put it in words so that it's not confusing. Like the vector of constants is 3, 4, 5. So I'm using the colors so that they match, right? So 3, 4, 5 matches like the constant, like well, like not the constant, the coefficients. Like, sorry, I meant coefficients, like the coefficients that appear in the optimization function. So let me call that the coefficient vectors. Okay, perfect. Now, what is the vector of constants? Like, what are the constants here? The constants here are 1.2, 1.7. But 1.2, 1.7 we're here, right? And actually, let me put the names here as well. There was. So I don't know if you're seeing that kind of like you're switching like the position where like everything appears, like like you're moving around like the pieces, but they're essentially the same pieces. So like the constants are, it's kind of like a pulsar where like the numbers that appear here were moved to the inequalities, right? And the numbers that appear in the inequalities were moved to the coefficients. So like it's kind of like like moving around all the numbers. Um, Is it okay, let me stop here. Everyone okay with me so far so good, like how we're doing this? And then comes like the cool part, like the next nice part, which is like what happened with the matrix, right? What is the matrix now? The matrix now, because now there are two inequalities, it is two rows, right? And there are three variables, so it's 2 by 3, right? So before, like, it was 3 by 2, and now it's 2 by 3. So but what is this matrix? It's literally just like the transpose of the previous one, right? You just transpose everything. Yes. Oh, sorry. Good. Thanks. Thank you. Yes, one. Perfect. Yeah, now it's good. Is that making sense? And okay, now let me write it in a way that's not specific to these numbers, like just like in general, what's happening. So in general, so what is going on here? So if you have again, like the primal problem, which is, sometimes that's called P. So where it was like, let me see if I can follow the, yes, it was C dot X where, X is greater or equal to 0, and AX is less or equal to B, right? What does the dual do? What is the dual? So the dual turns the max into a min. So instead of finding a max, you're trying to find a min. So you turn it into a min of what? The coefficients are no longer C, the coefficients are B. So you kind of like flip the positions. So you put B dot Y, right? Where Y is a non-negative, is a vector of non-negative variables. Okay. And the inequality, so you flip max into min, and you also will reverse the inequalities, right? Like, so instead of being a less or equal inequality, it's going to be, a greater or equal inequality. And here, so you're going to get that C is less or equal to A transpose times Y. Is that it making sense? So again, like this part is to, max becomes mean, inequalities get reversed, matrix gets transposed, and then you flip like the vectors, like the coefficients with the constant vectors get swapped. Like, like one becomes the other. Yes. Well, I mean, the thing is like in a dot product, right? In a dot product, it doesn't matter whether, like you write them as columns or rows. I guess you could have put that, like, if I keep writing the vectors, I could have written it as a transpose somewhere in here. Yeah, that's fine. Yeah, that would have been fine. But since I'm writing dot product explicitly, that kind of like gets like understood, like, but yeah, you could have put like, you could have written like V transpose here if you had wanted, but it's not like super necessary because like it's within, the important thing is like the numbers themselves, like the numbers get swapped in where they were located, right? But when it's kind of like when it's just like a one column or one row vectors, like it's like, that's more optional whether you want to put it with transpose or not. Um, is that making sense? Kind of some, is that okay? Questions about that so far, so good? So it's kind of like very like if you look at it, it's elegant, right? Like how you find one from the other. Like it's there's a transposition, and then like coefficients becomes constants, right? And if hopefully I'll put this more explicitly as a problem for you to think about. But since the transpose of a transpose is the original matrix, that should tell you that the dual, like the dual of the dual kind of gets you back to where you started, right? So I'll add it as I'll put that as an exercise for you to work on. But since so I'll make it as a remark. If you were thinking, if you thought of your dual problem as the original problem, the dual to that would be the max, like the primal one. So like everything gets like it's kind of similar to it's that's why I call duality, because it's kind of like a mirror, right? Like the mirror image of the primal is the dual, but the mirror image of the dual is the primal. So it kind of like goes back and forth. So okay. But again, I'll put that as an exercise because it's like a fun exercise to work out. Uh, is that making sense? Now where we are headed, like at least I'll put first where we are headed, and then I'll just mention something smaller, which we can do now in the minutes that we have left. But where we are headed is called the duality theorem, which says that if this problem has a max and this problem has a mean, they do agree. So like you have always like a perfect coincidence like of those two values. So like the maximum, you know, the number that maximizes here, like the function, which in this case in the farmer's problem was 8, would agree with the number that minimized the inequalities that we were playing with. So if you saw we had done like 10 point something and then 8.4, so like in fact in this problem you could have played with coefficients to get to 8. So the duality theorem says that if both are finite, then like they coincide like the values. So like the goal, like, and this will take a couple of classes. Because again, I do want to throw in some applications in the process to kind of make it more interesting. But the goal is to show the duality theorem. And this has like applications to game theory and other things, which I'll probably mention to you, like because they're kind of like fun. Is that which says that if so if like what the duality theorem says is that if you have a max to the original, if the max is achieved for the original problem, because sometimes like the problems could be unbounded. So you do have to make some cases later, which I'll write more precisely once we try to prove it. But if the max were actually finite and the mean were actually finite for these problems, then they would agree. Then those two values, these two numbers coincide. Then these numbers coincide. No, no, sorry. Okay, is that making sense? And now what the weak duality says, which we can prove today, is that um, I'll write it more precisely in a moment. But what the weak duality says is that the values, the values that you get here are always at least as big as the values that you get here. So if you have like different like points, you know, if you have different vectors, like, and plug in the function of those vectors, like the values for that function are always bounded below by, are always below the values that you would get from the dual, which is what was happening. If you notice, this is what was happening in our example. The numbers that we were getting were like 10.4, 8.4, etc. And those values are always above the values for the farmer's problem, because in the farmer's problem the most you could get was 8, right? So like so let me write that today, because it's like a 2-line proof. It's very cute, so like we can do it today. So what we can prove now is the weak duality. Which basically says, what does this says? That if you have two vectors, so what does weak duality says? It says, so it says that if you have a vector that satisfies the inequalities for the original problem, and um, you have another vector that satisfies the inequalities for the dual problem, then what should I say? Okay, so again, it works, and again, you'll see like it would take like 2 minutes to do, but it works. But it's what this is saying is that the values from the dual are always above the values from the original problem. Like the values that you of the function of the dual function are always above the values of the original function. So the values the dual function takes are above or equal to the values of the smaller function, to the values of the original function. Okay. So, the dual problem in a sense tells you how, how big can the original problem get in a sense. So why is this true? So it just uses like you just play with the properties of the transpose and the dot product. So let me show you why. And maybe let me give different colors here because I'll use these inequalities at different places. So okay, so why is it true? Let's start with the left-hand side. How do you prove an inequality? Well, you can start with the left-hand side and try to get to the right-hand side of the inequality, right? So what is C dot X? Again, the dot product is the same as X dot C, right? It doesn't matter in which order you place the dot product. Okay. And then if you, and again, this is why let's go back to reason one for why the transpose is nice. Reason one for why the transpose is nice is because you can use it to write a dot product. So again, when you have a dot product, you can just transpose the first factor. So I'll transpose the first factor. Just to drop the matrix, just to write everything in matrix notation, basically. That's what I want to do. Okay. But what can I say about the vector C? Well, I'll kind of like write the vector C here as well. So I'm thinking every vector here is being column vector, just in case, to make them. And let's see. Oh, like, yeah, let me drop the arrows because now I'm thinking everything as matrices. Okay. What can I say about the vector C? The vector C is less or equal to A transpose one. Why? That is what you have here, like by assumption. So let me use a color. That's why I wanted to use the colors. Right? So this is X transpose, A transpose times Y, right? But what is this? Like, remember, like the transpose, you can flip the order of the transpose if you transpose everything. Okay. But what can we say about AX? Let's see. AX is less or equal to B. So AX is less or equal to B. So this is B transpose Y, which is the same as B dot Y. Okay. Which is the one you had here. But you see, it's like not a particularly hard proof, but it's still clever because you didn't need to remember how to play with the transpose for it to come out very nicely. But at least what that says, what this is saying is that, again, you're trying to find the maximum for the original function. You have the values for okay, you're trying to maximize the original function. You're trying to minimize the dual function. What the weak duality says is that at least this one is really always above the original one. And the duality will say that is that they coincide at the max and the min. Like, that they actually are an equality. But that, as I was saying, like that does take a little bit more time. And what we are going to do Wednesday is start talking first about something called Farkas lemma, which is kind of like a mini step, like an important step in the duality theorem, And that already has some like applications to probability. I'll do, if I have time, I'll also do some applications to probability on Wednesday. I'll give you the basics of what you need to know, but it's like a very clever it's like a cool application. And let's just end here. And so if you have any questions about the exam, you can make a regrade request just in case.